I'm going to talk about a few things here. It is an absolutely massive topic. So I've just picked 3 areas which I thought would be interesting to talk through. And by the way, please feel free to jump in if there's any questions or comments. Just dive in, because it's everyone's got interesting perspectives to share around this. I thought it's first worth sharing just some perspectives on risk and probability, because I think understanding probability is central to understanding risk and the kind of techniques you'd want to use to do risk prediction. I'd like to talk about actually applying risk prediction, so some actually context, how you'd want to apply it, where it can be applied, some of the tips and tricks for doing that. And finally, I thought I'd just talk about some special considerations in the insurance market. And risk prediction's got its sort of nuances in different areas. Insurance is like any others. There's some special things you need to know about risk prediction insurance. So I was just going to highlight a few of those. Okay. So I'll start off with the the quick definition. So I've defined risk prediction as the process of estimating the probability of an outcome given limited information. And all of this is quite important. It is a process. There's not like a magic black box. You can just press a button and say, what's the answer to this question. It's an estimate. We're dealing with an uncertain world. It's about probability. We're trying to percentage chance of something happening. It's an outcome. Presumably, it's an outcome you're interested in. There's not much point, predicting the risk of something that's unimportant to you, and that's going to be clear in some of the examples we come to later. And it's limited information. No one has perfect information about the whole world, but I think particularly in the business and context, it's expensive to collect information. It costs your people time collecting it. It costs your data scientists processing it. It costs you storage. You may pay to get data. So you want to make the most of the limited information that you have. So I think it's quite interesting to start and say, okay, what happens when you've absolutely got no information? Mathematical definition, just the terminology. You've got the probability of some outcome given some information or some not so important, but just there's a whole notation behind this. So I think it's interesting to start with the situation where you have absolutely no information at all. So here's a question, which is, I think, it's quite an interesting question. What's the probability of outcome A? So throw it open. Who thinks it's 50-50? Who thinks it is a number other than 50-50? More. Who thinks that this is a question which cannot possibly be answered? Quite a few. Okay. This is actually, it is a hard question to answer. It's generally a subject of massive philosophical debate among, there's a group called the objective Bayesians who believe that the answer is 50-50. And they make the argument that you can make an argument from information theory, this idea of maximum entropy, that 50-50 is the only answer which really makes sense. And you can also make the argument from symmetry. So if A and B, you relabel them the other way around, it would be a bit odd if, the probability changed just because of the way you named them. So, there's a couple of reasons why you might think that. But, it's certainly not a settled issue. It's certainly a big philosophical debate. But, the whole idea is you've got to start from some kind of understanding. Then you get subjective Bayesians who believe that you can basically believe anything you like. Since there's nothing to contradict you, it's just a belief. Of course, when you start adding information in, your assessment of probabilities might change. So my question here is, are there any cookies left in the jar? And I've put my own subjective probability on this. Since I happen to know there's some cookies yesterday, and I believe my flatmate has not yet eaten them all, so I'm thinking there's a reasonable chance I get one when I get home. But I've not used any data there. Yeah, I've just got this sort of concept in my head, some intuition, which has enabled me to come to some kind of risk assessment. Yeah, and if you had some different information, you'd come to a very different answer. Like, suppose I told you that this cookie jar was in a kitchen shop on the shelf for sale. You're probably not going to get a cookie. And you use your knowledge about the world and your understanding of the world in order to build risk assessments. And you can do that in absence of any data sets. Yeah, you don't need data science to be able to do this. This is something that we can innately do, and you've always got some sense of what you think a probability might be. Of course, if you do have some information, you can gather statistics. Will it rain on a typical day in Singapore? I'm reliably informed there's about a 49% chance of an average day having rain. I guess that's true because it came from the internet. Once you sort of add information, you can refine your prediction. Yeah. So will it rain on a typical day in a known month? And again, reliably from the internet, there's a variation of percentages from 55 to 61. 39 to 61. And this highlights an important point. The more information you can bring to bear, the better your predictions can be. The more you can push it towards certainly yes or certainly no. And you can imagine if you had even more information, your predictions would get much better. Like if you could add whether it's raining in JB or not, might give you a pretty good prediction of whether it's going to rain in Singapore on that day, or what's the air humidity, or these kind of factors. So the more information you're able to gather, the better these predictions can become. But it's not all about stats. I mean, you actually have to understand some of the logic of probability here. So I have another quick question. So the situation: there is an outbreak of a dangerous virus in Singapore, and to quickly control the outbreak, they're going to go and test absolutely everyone to see whether you've got the virus so they can get quick treatment. Now, luckily, the test for this virus is pretty accurate. It's 99.9% accurate. So it gives the correct result 99.9% of the time, and it only gets it wrong 0.1% of the time. And the question is, if you get this test and it comes up positive, what is the probability that you actually have the virus? Okay, give us a second. So again, we'll do... Everyone got their answer? So a quick show of hands. Who think the probability is 99.9%? One. A couple. Who think the probability is below 99.9%? A few more. Who thinks the probability is above 99.9%? And unanswerable question. Okay. It could actually be any answer. There's not actually enough information here. It could actually be 100%. It could be that every single person in Singapore is actually infected and you definitely have the virus. It could also be that no one's got the virus and you just got a false positive result. So any answer between 0 and 100% is actually possible. The missing information is what's the base rate? Yeah? So what percentage of the population do you estimate to have the virus? And if you're given that extra bit of information, you can actually do the calculation properly. Yeah? So say there's 1,000 infected people, there's a base rate of 0.0185%. That means that given and then you can plot in a chart. You can say, all the different combinations, test is negative or positive, whether you're infective is true or false. And you can see that what's interesting here is that for the people who actually don't have the virus, in the 0.1% of people who get the wrong test result actually turns out more than the total number of people who have the virus in the whole country. So even if you get the positive test result, the odds are that it was a false positive, yeah, and that you're not one of the people. So in fact, in this case, it just works out as about 16%. But this is a really important point, because this is a fallacy. Yeah, our intuitive understanding of probability often fails us, and if you don't actually think about the problem and the particular risk that you're trying to predict, it's very easy to make a mistake. And there's been some quite tragic cases where people have been convicted on the basis of statistical evidence of this kind of nature, when in fact the chance that they actually committed the crime was actually pretty low. And some sort of miscarriages of justice have happened. Same happened to doctors. Yeah, doctors actually make mistakes on these kind of things if they don't actually understand the statistics. So it's kind of an important point to highlight. Ooh. So this is actually applying this prediction in practice. I'm not going to do the same thing again. So there's many different applications of risk prediction. I've just listed a few here that I've personally had some experience with. The point is, it's all the same kind of problem. Yeah, if you learn risk predictive techniques in one, you can sort of apply similar techniques in the other. So let's take health insurance. You might be interested in something like, what's the probability of an emergency hospital admission? Yeah. The data you might use is patient health records. So people who have a family history of stroke might have a higher chance of of hospital admissions. It's a kind of problem that's pretty important for health insurers to understand these kind of risks. And past claims, yeah, if you're looking at reimbursable health costs through insurance contracts. Fraud detection. And here the risk is that you don't notice a fraudulent transaction. You lose money, or you lose customers, or you have an impact on your operations. Looking at transaction information, merchant data, patterns of recent transactions. There's big money in this. So a company I worked with recently made over $75 million by applying fraud detection at their point of sales units. So it's you can make some pretty big money with and savings if you apply risk prediction in the right way and you figure out how to actually cut off the fraud at its source. Predictive maintenance. This is very interesting again. So I worked with a telco that was interested in the probability of particular pieces of equipment failing. So imagine network equipment. And if this equipment fails at the wrong time, with the wrong kind of load on the network goes down. They lose a lot of revenue because they know the customers can't transmit data over the network. If they can predict what's going to happen and then they can replace the component before it fails, or very shortly after it fails, then you're in a much better situation. Again, it's a pretty big economic advantage. Spam prevention. Now these are small losses. Yeah, it's not actually the biggest loss in the world if a single piece of spam goes through. But on the other hand, if you add up that loss over the entire population, it's pretty significant. So again, it's another kind of risk. What's the risk of stopping a wanted piece of mail versus letting through an unwanted piece of mail? So there's sort of a cost-benefit trade-off that you want to apply to large scale. Social network recommendation systems. You can predict whether someone will actually like a particular product or a post or some other activity on a social network. It's a kind of technique that Netflix would use to make film recommendations, or Amazon might make in terms of recommending a next product to buy. It's interesting as well because there's some risks around this in itself, in the sense that if you're always recommending things that look likely, then you maybe get homogeneity. Yeah, so people always get given the same things, sort of things that they've seen before, and you sort of get these sort of clusters of people who only see the same kind of things. So there's the general approach, and for all of these kind of problems, and if there's one thing that I think is important to take away from this talk, it's this approach. Yeah. And if you're going to actually get value out of risk prediction, you always need to do these three things. Yeah, you have to get the data, you have to extract the insights from the data, and it has to lead to some kind of action. I've seen so many times there's all this fantastic analytics, and you ask, "This is great. How did it work? What actually was the impact on the ground?" Oh, we never rolled it out. Yeah, and you have all these beautiful visualizations, it's really important to take it all the way through. Yeah, so you've got the data, you've done your predictive modeling, you've calculated all the risks, and then you've got to do something to actually get the value. The process is fairly standard. You've got some kind of data acquisition, you've got to identify the right data sources that you think are predictively useful. Yeah, so what are the things you think are going to be correlated with the risk? Ensure you have an unbiased sample. This is actually a bigger problem than people realize. It's very common that you have, for example, only occurrences of the risk. If you don't have the non-occurrences, then it's possible to have a very, very biased data source. So you need to make sure you've got the complete population represented in your sample. Otherwise, your risk predictions are going to be very, very weird. You need to clean and transform the data, and you need to confirm that you have the right legal rights, so privacy, data protection, particularly if you're doing individual level risk prediction. To get the actual insight is typically about predictive modeling. So you'll have to choose a predictive modeling approach. I mean, you can use neural network type models, you can use a regression, so logistic regression. You may want to perform some pre-processing in order to make the model work, so kinds of feature detectors. You want to build your model using the training set, so you want to some of the data, and you probably want to check the performance of your model if you're doing your data science properly with a validation or test data set. So you want to confirm on unseen data that your model is actually performing well. And then finally, in terms of actually applying it, probably you're going to have to modify a business process. Yeah, what are you going to do with the fact you've got a predicted risk? So, for example, you may produce a list of the 100 most likely fraudulent cases and hand it over to a team who's then going to do a deep dive and do the private investigator stuff and figure out what's actually happened in each of those cases. But in some way, there's some business process change involved with realizing the value. You're probably going to have to think about, do you integrate this risk model into an IT architecture? Sometimes it makes sense to do standalone analysis, but often, you're going to want to do real-time predictions, so you have to find a way to actually build the solution in. And you want to continuously monitor performance. It goes without saying, if the model's working, if the model performance gets worse over time sometimes, you're going to want to think about recalibrating the model. Very important to keep a track on what's going on in practice. This is my favorite technique. I like neural networks as a solution for risk prediction. The way these work is you've got a set of input data, so all the information that you have about the risk that you're interested in, and you encode that in like binary ones and zeros, and you feed that into this network of connected nodes. And each node is performing a calculation. And if you calculate up this stack, at the very top, you get a probability out. And there are some techniques, some algorithms you can use, which I won't go into, but to create a neural network like this, that comes up with some pretty good risk predictions. It's actually quite a good way of getting a useful model out of quite a wide range of different types of data. Just a tiny bit of maths. The key way that a lot of this works is you have this, each node is performing a little calculation. And the way it works is it's adding up the inputs which come into it, and it's putting it through this special function called a logistic function. So that you can see the fx equals the sigma of the sum of, I don't know quite what it's done to the formatting there, but it's meant to be the sum of the inputs. And this little sigma is the logistic function, which is defined as 1 over 1 plus e to the minus z. Again, the formatting seems to have gone a bit weird there. And it looks like this. So it starts out at 0, and as you get to a 0 total input, so when all the inputs balance out, you get 0.5 as an answer, so 50%. And if you get to about 6, you're getting very, very close to 1, so 100% probability is the interpretation. And I like to think of this as accumulating evidence for or against the risk happening. Yeah, so that's just my mental model. It's may or may not be useful, but personally I find it it's like a scales where you're weighing up the positive and negative elements, and the logistic function kind of represents that. This is how you might build this kind of thing, and this is an example from actually healthcare risk prediction. But a typical sort of IT architecture that you'd have would be a number of different source databases, source data sets, pulling that into some kind of analytical data store. You then do the data science slightly to the side, where you actually analyze the data, understand its properties, really think about the kind of probabilities and the sort of the different factors of risk and the problem that you're solving, so that you can design a good model. Once you've got that model, you can apply it to your data sets. You can create an augmented data set with risk scores. So maybe you're interested in finding out who are the 10% highest risk patients, so that you can take some special disease management measures, for example, to reduce the chance of emergency hospital admissions. And once you've got those augmented risk stores, you can then use that in a number of ways. So you might be doing some risk analytics, understanding the overall health of your population, or you might producing operational reports. So look, these patients seem at particularly high risk. Let's make sure they get some special treatment. That makes sense to everyone. That's obviously more of a sort of a batch one. You can imagine the same kind of thing, but done in real time. So that as new cases come in, like in a fraud transaction, you'd look at each new case, run each case through the risk model in real time. Finally, I'll just go through some special considerations for insurance. Might be interesting. Adverse selection is fun. And the reason I find this interesting is when you actually participate in a market, you change the way that the market behaves. And how this manifests itself, let's say you've done a whole load of research and you've understood the distribution of the risk levels in the population that you're dealing with. And you've got some idea of what the average risk level is. As soon as you start selling insurance on this basis, what you'll find is that people who are higher risk sort of know that they're at higher risk. You know, they're a bit more worried, you know, that this maybe happened in their family. They know things that you don't necessarily know, and they're more likely to buy your product than the general population. And what you'll find is the population of people who buy your product tend to end up in a much riskier, on average, than the general population that you analysed. And this is a pretty big risk, yeah, because if you price your insurance product on the basis of the average in the population, then you're going to end up making a loss just because you ended up getting all of the people who sort of self-selected in and realised that they were at high risk. So it's particularly, it's because there's choice, ultimately. There's agents, independent agents making a choice based on your action in the marketplace creates this opportunity for adverse selection, and you don't necessarily have the, you know, quite as much information as they do. So you know you can't head this off very easily. So that's why the insurance product design is much more than about just calculating an average risk. Another problem you tend to get is very small sample sizes. So particularly if they're low risk events, even if you've got quite a large population, quite large number of policies, you may only get a small number of claims around a particular kind of event. So here, you know, imagine you've got only 3 claims in the data set. It's quite hard to draw inference from that. You know, it's going to be probably statistically insignificant, whatever you do. So are males twice as dangerous as females in terms of this kind of claim? You know, maybe, but you know, you haven't really got enough information to draw that judgment conclusively. Or maybe it's people in their mid-20s are actually the most dangerous. You know, there's too many possible explaining factors and not enough data to describe it. The hard bit is you may actually have to offer a premium on certain kinds of risks. So if you imagine people underwriting quite unusual risks like, you know, shipping, there may not be that many shipwrecks per year, but there's still a market for selling shipping insurance. So there's a lot of judgment and skill for underwriters in being able to judge these kind of risks and put appropriate pricing. Finally, and I think this is, you know, particularly important when you look at the sort of life insurance aspects, is you've got regime shifts, so structural change in the way that the world is behaving. So if you look at the evolution of life expectancy, for example, from, I think this is the UK, from 1841 to 2001, what you see is the way that you would predict life expectancy has changed over this time. The historical evidence shows that people are living longer and longer and longer on a number of different measures. And something's changing in the world. If you built your model in 1841, it would be wrong in 2000. Significantly wrong. You know, you'd probably lose quite a lot of money again. And you need to anticipate these structural shifts so that you can watch out for them and make sure your model is still continuing to perform. It's a very important aspect, particularly when you look at time series data. If you dive in, you'll see some interesting attributes of that. So actually how the number of survivors by age evolved. And what you see is that, you know, sometime around between 1900 to 1950, what happened is a lot of very early age mortality, and that basically got eliminated, and that sort of shifted these life expectancy curves up. So something happened in terms of, you know, modern medicine, in terms of antibiotics, which has sort of resulted in these quite big shifts. And it's not going to stop. Yeah, you can imagine life extending treatments in the future, genetic therapy, you know, new ways of treating previously incurable disease. are going to continue to shift this. Some of these will be back spawns, things you don't expect, and that's part of risk prediction. Yeah, it's not just a single statistical technique you can just apply. You actually have to use your understanding of the world to predict risk well. And to me, that's part of what makes it fascinating and what makes it a great challenge. So, hope you found it interesting.